Team Doctor, and we're dissecting a bike pump.
Our bike pump is specifically a dual action pump, meaning that the pump generates output airflow on both the downstroke and the upstroke. The dual action design together with one-way valves, the pump is able to maintain continuous volumetric airflow. The main chamber behaves as a piston cylinder container with a moving boundary. Inside the main chamber, we found two inner cylinders, each with its own one-way valves. On the upstroke, the control volume increases within the inner cylinder, creating a pressure lower than ambient and inducing airflow. However, due to the increased amount of air in the pump as a whole, the pressure in the outer cylinder increases, and the air is then pushed through the outlet valve in the outer cylinder. During the downstroke, the action is reversed. Thus, by controlling the pressure inside the pump chamber, we are able to take advantage of the dual action behavior. This pump is an example of a positive displacement pump, as each inner cylinder encloses a fixed control volume of air and displaces that volume through the system.
To start our analysis, we remove the base plate cover by hand and then use a screwdriver to take out the seal, which exposes the pump's inlet and outlet check valves. After that, we unscrew the top cap, which lets us see the handle mechanism. This mechanism uses a piston and an upper cap to pull air into the main cylinder during the upstroke. Taking off the cap also revealed two inner cylinders inside the body, each connected to the inlet and outlet valves. We remove the hose from the outlet port by hand. When the handle moves, it drives the piston up and down, creating low and high pressure inside the cylinder. This pressure change draws air in during the suction stroke and pushes out during the compression stroke. The airflow flows through the inner passages, through the valves, and leaves through the outlet port into the hose. The seal and gasket help prevent leaks, allowing the pump to maintain pressure and work efficiently. These measurements will help us perform more detailed calculations later on about the pump's efficiency, flow rate, and operating speed.
The pump has connecting tubes that function as short pipe with check valves. Flow through these passages is driven by pressure difference rather than by external free stream effects, and the air remains confined within solid walls throughout the process. As a result, the pump is fundamentally a container pipe system governed by unsteady internal flow and the conservation of mass and momentum rather than an airflow type flow device. The equation used is Bernoulli's equation, where pressure divided by rho describes the pressure unit per unit mass, v squared over 2 described by the kinetic energy, gz described by the gravitational potential energy, and hl describes the head loss due to the friction. This equation is only applicable due to the assumption of incompressible flow. This equation helps us understand how the pressure energy generated by the piston is redistributed into flow kinetic energy and dissipated through losses in the tubes and valves before the air reaches the tire, explaining both the required pumping force and the pump's efficiency. Assumptions: we assume that there's an incompressible flow, Mach number of way below 0.3, that Z1 and Z2 is about the same, it is quasi-steady flow, and we assume that the force is of the push 50 newtons.
The pump's behavior is governed mainly by the Reynolds number, which tells us how turbulent the airflow inside the hose is, and by the pressure-volume work equation, which tells us how much force the user must apply. In a bike pump, we calculated the Reynolds number to be around 2500, meaning the flow is probably intermittent, which is true, and friction losses matter. We can still use the Darcy-Weisbach equation for intermittent flow by applying it to the instantaneous flow velocities during each stroke, treating the flow as quasi-steady. Using these parameters, we can explain why the pump is designed the way it is. If the piston diameter were double, the stroke volume would increase fourfold, but the user would need 4 times the force, making the pump unusable. If the hose diameter were doubled, the friction losses would drop to about 1/30th, but the hose wouldn't seal on the valve. If the hose were sharply curved, then losses would spike and pumping would feel harder. And if the internal surfaces were rough, friction would increase and efficiency would drop. Finally, if the working fluid had a much higher viscosity like honey, the Reynolds number would collapse to nearly zero and the pump simply wouldn't work. So, all in all, every part of the pump is sized so the pressure is high enough for the tire, but still low enough for a human to push.
Let's do an example calculation. We have some relevant dimensions, and we have this great equation, but we can cut a lot of them out using our assumptions, so we get some more easy to work with numbers. We can simplify this down to find our velocity as u2, which is all these numbers. However, f is dependent on our Reynolds number, which is dependent upon our velocity, so we have to iteratively find a new velocity. Finally, our efficiency. The efficiency is equal to the change in pressure over the total pressure we input, which is 96%. We could cut